Alright, in this video we will be talking about simple machines. So hopefully you've learned in the past that there are 6 different types of simple machines, and they are just small parts that can be used to build bigger machines. And the purpose of a simple machine is to change either the force or the distance or direction that a task is done. So the 6 types of simple machines are the lever, wheel and axle, pulley, inclined plane, wedge, and a screw. Okay. Now, a lot of times with wheel and axle, especially, people think the only example they can think of for wheel and axle is like the wheel of a car or a wagon or something like that. Well, a wheel and axle really is, in terms of simple machines, is probably better to be thought of as things like gears on a bike, or like on the example here, the crank to lift, say, like a bucket of water out of a well. Okay, so something where you actually put a force on the wheel, and then the axle puts on a different force. So a wheel and axle in a car is a simple machine, but that's not the type of way we usually use it for these calculations. Same thing with a screw. A lot of times the only example of a screw that people can think of is a screw like you screw into a piece of wood or into a bolt, and really screws are much more than that. Screws are anything where a rotational motion is turned into a linear motion. So even like the fan is a screw. So the blades turn around and it turns the motion into a linear motion of the air. There's a couple different formulas that go with simple machines. Simple machines, we oftentimes talk about the mechanical advantage, which we abbreviate mechanical advantage MA. I guess it doesn't help to illuminate it very much. Yellow on top of blue. Let's see here. Okay, so MA, the mechanical advantage is equal to the force that you get out of the machine divided by the force you get in. So oftentimes simple machines are used to multiply the amount of force you get in, or to a certain amount. So if you only lift 100 pounds but you need to lift 400 pounds, you use a simple machine, and then you set it up such that it can do that. Now, one thing with simple machines is sometimes we do end up making the force smaller, and that's usually because we want them to go a greater distance. So like, for example, when you are riding your bike and you're in a high gear, you have to put a lot more force in, but then your bike goes a lot faster because you have a very small mechanical advantage. The next equation here talks about the IMA, which is the ideal mechanical advantage. That's the mechanical advantage a machine would have if it was 100% efficient, which if it was a perfect machine and using it didn't have any friction involved and didn't have any like bending or stretching or flexing, okay, you would get what's called the ideal mechanical advantage. And the ideal mechanical advantage is equal to the distance that you get out of the machine divided by the distance you put into the machine. So for example, in this lever over here, if you were to move down on the effort side of this lever, if you were to move, let's say 5 meters downwards, that's a big exaggeration, I don't know, you pulled on a lever that far, you would on the other side maybe only be able to move it up 1 meter. I guess I better pause as I get the phone. Alright, and then back. So with the lever then, if you're pulling down 5 meters and it's only going to lift the load up 1 meter, then you are multiplying your force ideally by 5. Now if the lever bends or stretches, that's going to reduce it some, because when you pull down 5 meters, it might not actually lift it up 1 meter as the lever bends. With any simple machine, at best, so so in an ideal machine, the work that you put into a machine equals the work out because of the law of conservation of energy. But because some of the work you put in is going to go into things like heating up the machine because of friction, or storing energy into the machine because of the bending and whatever, the work out is always going to be a little bit less than the work in. Since work is force times distance in an ideal machine, you can say the force in times the distance in equals the force out times the distance out. Because real machines aren't ideal, we measure what's called the efficiency of the machine, which is the work out divided by the work in. you can show through some math that the efficiency can also equal what the mechanical advantage of the machine actually is, divided by what the ideal mechanical advantage of the machine should have been based on how it's designed. We can look at ideal mechanical advantages for the different devices by for a lever, the ideal mechanical advantage equals the length of the effort arm divided by the length of the resistance arm. For your wheel and axle, the ideal mechanical advantage equals the wheel diameter divided by the axle diameter, or wheel radius divided by axle radius. For a pulley, the ideal mechanical advantage equals the number of supporting strings. So for example, for this pulley shown here, it has 2 supporting strings, so its mechanical advantage would be 2. For an inclined plane, the ideal mechanical advantage is the length of the plane divided by the height it lifts the load. For a wedge, the ideal mechanical advantage is the length divided by the thickness. And for a screw, the ideal mechanical advantage is the circumference divided by the spacing between the threads. So using those equations, let's work some example problems. So the first one, we have a lever with an effort arm of 50 centimeters, and it's used to lift a weight that is 5 centimeters away from the fulcrum. So we have a lever. Boy, I'm just really having a bad luck with colors today. We have a lever, and it says the effort arm, so that's where you're going to lift from, is 50 centimeters long. So here's you. And then you're going to lift a weight that's 5 centimeters away. Okay, so this is obviously not drawn to scale. If the weight that you're lifting has 10 kilograms, we want to know how much is required to lift the block. Okay, so again, the ideal mechanical advantage, and we're assuming this is a perfect lever because it doesn't say anything else, is 50 centimeters divided by 5 centimeters. So ideally, we can lift 10 times the force here. It's a 10 kilogram block, so the weight of that block is equal to mg, so it equals 10 kilograms times 9.8 meters per second squared. So that equals 98 newtons. And if the ideal mechanical advantage is 10, then in a perfect machine, the ideal mechanical advantage equals mechanical advantage, which equals the force out divided by the force in. We want to get 98 newtons out, and so if we solve for what force in has to be, force in would be 9.8 newtons because the machine multiplies our force by 10. A pulley with 4 upward supporting strings is being used to lift a load. If 10 newtons of force is required to lift the load, how much does it weigh? So if we have a pulley, and again, since it doesn't say a pulley system actually, so basically what happens is the string wraps around. So we have a total of 4 strings, and then we've got our load here. If we're pulling with 100 newtons of force, because there are 1, 2, 3, 4 strings, the ideal mechanical advantage of this system is equal to 4. And so then, because it's a ideal pulley, because it doesn't say anything, our mechanical advantage was assumed to also be 4. So the mechanical advantage is equal to the force out over the force in. The force we're getting out is what we don't know. Mechanical advantage is 4. We don't know what force out is. And force in is 100 newtons. So force out must equal 400 newtons. An inclined plane is being used to move a refrigerator into the back of a truck. So we've got, here's our truck, it has some wheels, it has a plane going into it. The plane is 4 meters long, it lifts up 1 meter in height. We're moving our fridge weighs 800 newtons, and it takes 250 newtons to push it into the truck. Okay, so we want to know what is the efficiency of the ramp. So efficiency can be solved in a couple different ways. The easiest way, I think, to look at efficiency in most cases is comparing the mechanical advantage to the ideal mechanical advantage. So here we have a mechanical advantage is related to our force out divided by our force in. So we are putting 250 newtons into the job. We're getting 800 newtons out because the job is to lift that 800 newton fridge. So we have a mechanical advantage of 3.2. Our ideal mechanical advantage is the distance in divided by the distance out. We have to put a total of 4 meters in to move up the ramp. You get just 1 meter out, and so that's 4. So the mechanical advantage, the efficiency then would be 3.2 divided by 4. So that would be 80%. A man is rowing a boat. The oars of the boat are 3 meters long. So we have an oar. Whoops, forgot to curve it back in. So we have an oar. And the total distance there is 3 meters. Away from the oar locks, the man pulls on the oar with an effort force of 500 newtons. So there's 500 newtons here. And want to know what will the force on the oar put on the water if it's 90%. Sorry, it's 0.5. The handles are 0.5 meters away. There. Okay. So what force will it put on the water here if the oar is 90% efficient? So again, if we look at the efficiency is equal to the ideal mechanical advantage, or is equal to the mechanical advantage over the ideal mechanical advantage. For the ideal mechanical advantage, it's going to be, again, remember your distance that you put in, so 0.5 is what you put in, divided by the distance you get out, so that's 3. So your ideal mechanical advantage is equal to 0.17. So to find your mechanical advantage, you put that in. Your mechanical advantage, if it's 90% efficient, would then have to be 0.15. So 0.15 is equal to your force you get out divided by the force you put in. The force you put in, so the man is pulling on with an effort force of 500. So if we look at what was the force out have to be, it would be 75 newtons out. Now again, this is one of those examples where an oar of a boat is designed to get more distance out, so you pull a little ways and it moves the boat farther, not to get more force out. Okay, so we'll work a couple more problems in class and you'll have time to work on a worksheet and hopefully you'll get this all straightened out.